it is a wormhole sourced by a nonlinear electromagnetic field. And so this is a basics on wormholes and some comments about why the gravity in 2+1 dimensions might be interesting. Then in this system, in this solution of wormhole, we construct the Kruskal diagram and the Penrose diagram. And finally, we also perturb the wormhole with a massive scalar field, and we solve exactly the Klein-Gordon equation, and find the quasi-normal modes that are the response of this scalar field in the background of the wormhole. So first of all, I am going to comment on why these systems might be interesting. So the most famous solution in 2+1 gravity is the so-called BTC black hole. This is a black hole that occurs in two special dimensions and one time. And the characteristic of this solution is the cosmological constant. Yes, so before considering the cosmological constant, no one has found a solution, a black hole solution in 2+1 gravity. But the cosmological constant has the effect of this, the collapse can occur in these dimensions. So this is the line element of the black hole, BTC black hole. There is a horizon, of course, and the curvature quantities are not singular at r equals 0, but it is considered that at the origin there is a causal singularity, because they appear closed time-like trajectories. So I depict here the Penrose diagram, and this is, if you remember, the whole space-time concentrated in a finite area. So the red dashed lines are the horizon, and the blue is the causal singularity. The black lines are the infinities. So the black hole is considered from let's say the diagonal, the upper part of the drawing. So let's consider that in one of these spaces we send a particle. The particle will, let's suppose, that is relativistic, and that is trajectory is well approximated by a light ray trajectory. So the particle will fall into the black hole. The black hole will therefore have more mass, be more massive, and consequently its horizon. In anti-de Sitter, yes, the red lines and the causal singularity. So anti-de Sitter is just the black straight lines and infinities in the upper and lower part of the diagram. So the horizons are the difference and the singularity. And so I was saying that the new horizon is larger than the previous one, and this is the amount, the that the horizon grows. And now let's suppose that we take two of these systems, one with H horizon and another with H tilde horizon, and we put it together along a light trajectory. Now, if we have this system, we're taking care of the appropriate continuity conditions. When we send a light ray in this system that is a patch, let's say, of two black holes, the light trajectory will be like this. Yes, the lower part is the one with the H horizon, and the other one has a bigger horizon, and so the light ray will penetrate deeper. And this is interesting. But how about we send, instead of positive mass or positive energy to the black hole, negative energy, right? Then the diagram will change, and the light ray will be, instead of being deeper inside, it will be in the outer space of the other black hole. So in this process, it is created a wormhole. Yes, a wormhole that sends, or that a light ray can traverse in this way. And then in this way, we have created a wormhole. And this is a way of constructing wormholes. Well, along these lines, in a quantic way, there are currently being investigated the process of sending information, and Maldacena, for instance, is working on this kind of ideas in a quantum framework. Okay, so let's back to my work. This is one of the examples of why gravity into +1 dimensions is interesting. There are other features that I am not going into detail. For instance, the VTC black hole is very well characterized in the holography conjecture, and for instance the teleportation process, like the one I talked about, quantic. Okay, now to create a traversable wormhole, we need a special kinds of matter. The one that is not attractive but has the opposite characteristic. But this sounds odd, but there are several fields. Okay, thank you. Thank you. There are several fields that have this kind of negative energy, let's say, locally. For instance, some linear electromagnetic effects, or other quantic fields. I am going to take this action, that is the Einstein. This is the Ricci scalar, this is the cosmological constant, and this will be the matter that will open the throat of the wormhole. As I told, including the cosmological constant is a key factor to have this kind of structures like black holes or wormholes. This is the kind of topology that forms the appropriate topology, let's say. So we have the Einstein equations, and the electromagnetic energy momentum tensor is given in this way. In regular electrodynamics, we have here just F. F is the invariant, the electromagnetic one of the electromagnetic invariants, and so this is 1 in regular electrodynamics. I am going to take here nonlinear electrodynamics, a special kind of nonlinear electrodynamics, because this is not defined. I am just saying that it is nonlinear. It's a Lagrangian nonlinear on the electromagnetic invariant. So there are outstanding nonlinear electrodynamics are the Euler-Heisenberg electrodynamics that was derived taken from quantum electrodynamics, and describes some nonlinear electromagnetic effects like light scattering, for instance, in an effective way. They are classical Lagrangians, but described in an effective way nonlinear effects. These effects happen under very intense electromagnetic fields. In non-so strong fields, we have the normal, the regular Maxwell electrodynamics. So the other one is the Boring-Feld electrodynamics that is given in this way. It was proposed in the 30s with the aim of not having the singularity in the field in the position of the point charge. Okay. Moreover, the Boring-Feld action arises also in string theory, and it is the effective action for low energy degrees of freedom of a big brain. Okay, I'm not going into details, but it is just to say that there are interesting nonlinear electrodynamic Lagrangians. So as I said, we found a solution to the Einstein equations that can be interpreted as a wormhole. So this is the line element characteristic of a wormhole in 2+1 gravity. There is a function that should never be 0. This is not a black hole. And there is another function that defines or determines where the throat is. It is where this quantity diverges, and so B at the throat is equal to precisely 1, and this diverges. Another characteristic of a traversable wormhole is the condition that the throat keeps open. So this is, if this is fulfilled, then you will have the throat, this throat will keep open. And this condition is related to the violation of one or more energy conditions. For instance, through the Einstein equations, we can connect the geometry, of course, and these conditions are related with the energy momentum tensor in this way. So this quantity means that an observer will see an energy density that is not positive. Okay, there are several fields that violate this. Well, this is the violation, no? Less than 0. the fulfilling of this condition is this being positive. No. It depends on the signature. So this is the null energy condition. Okay. So, okay. Okay, so the solution we found is a very simple one, and the electrodynamics we use is this one, is the electromagnetic invariant square root. So this is the solution, and it is singular at equals 0, and is characterized by the mass, the cosmological constant, an electromagnetic parameter, and that's all. So the field is located here, and what else? Well, it never happens at horizon, and the flying out condition is fulfilled. It's just a simple calculation, and consequently, the null energy condition is violated. Okay. Okay, yes, some details, but they are not very important in this talk. This is the electromagnetic invariant, and this is the component of the field that is non-vanishing. As I said, the flying out condition is given in this way, and putting this into the Einstein equations give us this, and connecting with the energy momentum tensor through the Einstein equations amounts to this. So we can check that this is the case in our solution, and so we have a traversable wormhole. Well, now we constructed the Sekeres, the Kruskal Sekeres and the Penrose diagrams. So I will go to it in this what follows. I don't know if you notice that GRR diverges at the throat. So we change to the R star coordinate or tortoise coordinate, and in this coordinate the metric looks like this. So it is important this coordinate because two factors. In this way, the metric, the light trajectories are just cones like in Minkowski, right? Are cones with a slope of 45 degrees. And the other interesting feature of these tortoise coordinates that are not exclusive of this system, but I mean, you put the metric in this way and define the corresponding tortoise coordinate for your metric. The other characteristic is that in this coordinate, the singularity of the coordinates at the horizon, or in this case, at the throat of the wormhole, goes to infinity, and it can be seen in this plot. This is the third, and as seen in the R coordinate, it goes to infinity. But when you put in the R star or tortoise coordinate, it goes to minus or to infinity. Right, so many things are easier in this coordinate. And this is the first step when one wants to construct these diagrams that the first one is the Kruskal diagram. This diagram extends space-time beyond the wormhole, and is this, let's see, the R coordinate, its range is from the wormhole throat to infinity. And extending to the tortoise coordinate, we go beyond the 12, but not but it is not the complete space, right? And so we make some coordinate transformations to get a manifold that is beyond the wormhole throat. So the critical coordinates are these capital X and T, and well, it is a process to construct this or to make the corresponding transformations. And in these coordinates, we extend the space-time, as I said, beyond the throat. This is the coordinates X and T. So in these coordinates, the red hyperbole is the throat. This other hyperbole, but imagine it is at infinity. I draw it here, but it is really at partial infinity. And this is time infinity. This is also time infinity. And we have in here the extended space-time. This diagram is also the basis to construct the Penrose diagram. That is the compactification of the whole space-time. So taking this T and capital T and X, we really this is the process of compactification to change some coordinates that go to infinity into coordinates that are located in a finite strip. Like in this case is the inverse tangent. Okay, so in these coordinates, this is the metric, and these coordinates lambda and rho are the Penrose coordinates, or are the appropriate coordinates to draw the Penrose diagram. And this is it. We have in here the infinities in the blue lines. The red line, this one is the throat. These are the time, past infinity and future infinity time. And the light ray will have this trajectory that is coming from infinity past the throat, and at the other infinity it can be reversed and so on. So this is the Penrose diagram. And finally, to complete the study of our system, we perturb with a massive scalar field. And so let's consider this is a generic perturbation. We have some center of some source of gravity, and we perturb with a plane wave. So in this case, well, just to recall what are the quasi-normal modes. The quasi-normal modes are the modes that arose when a perturbation interacts in a curved background. It may be a black hole, or in our case a wormhole, or any other gravity source. So, for instance, these are the frequencies or the eigenvalues of the perturbation equation, and these are called quasi-normal modes because, for instance, in a black hole we don't have a closed system, right? When we send matter or waves to the horizon, it gets lost. So the frequencies are not real. The imaginary part is telling us that there is some loss of the energy, and so that is the reason of the quasi-normal modes. So for instance, these are important in the collision of black holes. The ring down part, this last part, is get by perturbing a curved black hole. The real part is related to the frequency of the oscillations, and the imaginary part related to the damping. As you know, this kind of diagrams were important to the recent detection of gravitational waves. So in our case, we are going to ask a massive scalar field to interact in the wormhole background. So the equation for the scalar field is the Klein-Gordon equation in the fixed space-time curved by the presence of the wormhole. So this is the perturbation that we send, and into the Klein-Gordon equation we get some kind of second-order differential equation that in this case it looks like this. When we put this equation in terms of the tortoise coordinate, it looks like a Schrödinger equation, and then it is well, we can apply all the knowledge from quantum mechanics to solve this kind of Schrödinger equation. Of course, we have to apply the appropriate boundary conditions, and in this case, at the throat, we consider that there are only ingoing waves, and at infinity, we have to take into account that at infinity we have de Sitter and de Sitter space. So we ask that at infinity the perturbation disappears, right? So applying these boundary conditions, we solve the equation, and well, in here I am writing the effective potentials of the Schrödinger-like equation, and this is in the L coordinate. This is in terms of the tortoise coordinate. And when we put the equation in terms of the tortoise coordinate, we recognize this potential as well, half, because the range of the tortoise coordinate does not cover all the space-time, but it is a potential of the Rosen-Morse type. So we can solve in exact way the equation for the perturbation. This is the solution. And the most interesting part, of course, are the eigenvalues. Well, I'm depicting here the potentials. When seen in terms of the L coordinate, it's like a harmonic oscillator potential, and these red lines are the throat of the wormhole. And when we put the potential in terms of the tortoise coordinate or the rho coordinate, that is, it's proportional to the tortoise coordinate, we see the form of the Rosen-Morse potential, and this is the throat, right? So, the tortoise coordinate covers from the throat to infinity, but in terms of the extended potential, we can see the whole well, right? This is a potential that is an infinity, very well. This is a harmonic oscillator potential, and therefore we can guess what kind of eigenvalues or normal frequencies will have our problem, right? We will have a real spectrum and discrete. And that is in fact the case. We have in here the quasi-normal modes, but we can also call normal modes, because as we see they are purely real and nothing is lost in this system, right? We send a propagation and it passes the throat and goes to the extended space, and well, we don't have a complex frequency. Just to compare, I put the frequencies obtained in the case of the BTC black hole, that as you see, it has a real and an imaginary part. And this is related with the decay of the perturbation, with the time of damping time, right? Okay, I just depict the frequencies in terms of the mass, and for the modes 0, 1, and 2, right? For 0, this is the most important. And as you see, there is no much structure, but okay, to L greater, it is clearly discrete. Okay, yes, I came to the conclusions. So we study a solution that is a cyclic, symmetric 2+1 dimensional traversable wormhole, as we saw. The field is a nonlinear electromagnetic one with a Lagrangian given in this way, and the presence of the cosmological constant is important. Okay, I showed you the Penrose diagram that is in agreement with the information that we obtain with the quasi-normal modes in terms of the trajectory that perturbation of our light ray will follow. It will traverse the throat and will come out in the standard space. This nonlinear electrodynamics many times violate the energy conditions, or some of them, and this is important to, in the case of wormholes, to keep the throat open, or there are solutions of black holes that are regular, and okay, this will be the topic of another talk. And okay, there is also the next thing that we can go all the way through in an exact way. It's not easy to find systems where we can find in exact way the solution of to obtain the quasi-normal modes. For instance, in black holes, it is we use the blue cap B approximation, and they are numerically calculated even in the simplest cases like care or well. And so we don't know if this system will be of use or will have any interest in, as an example of the ADS-CFT correspondence. So this is the reference of the work if you want more details, and thank you for your attention.
Boundary conditions. So is this something you obtain, or just
no, it is just for well, what we can see clearly is that light trajectories will be these straight lines, right? But we don't know if it will reflect. This is not I think an exact result, right? But this one, yes.
More questions? Comments? Suggestions? Anything? I have a question. I guess this is not a unique solution because you are imposing some sort of spherical symmetry. You have a highly nonlinear field. So it is not expected that you have a unique solution. Can you say something about that?
About unicity?
The uniqueness of that.
Uniqueness? Well, when one deals with cyclic static solutions, there is a classification of the allowed electromagnetic field components. So, with Lagrangian, it is the solution. But we can have another branches of electromagnetic field and other possibilities of fields with other field components. I mean, this is a kind of electric field. We can consider an electromagnetic field with magnetic components. Yes.
So, more questions?
I thought these were electrovacuum solutions. Am I wrong?
Well, I wouldn't call like this because we have, if you call this electrovacuum is for Maxwell, right? Oh, well, if you call this Lagrangian electrovacuum?
No. Electrovacuum is a property of the solution, not the Lagrangian. And it's when the electromagnetic fields, even though your theory has them, are turned off.
No, but we always have the electromagnetic field. Yes, because if we don't have the electromagnetic field, this is the electromagnetic parameter. So we don't have solution. If we turn off the field, this becomes zero, and well, we don't have this solution. We obtain, in fact, a more general solution that can be interpreted as a black hole, depending on the ranges of the parameters. But, well, this one is particularly simple, and we could solve for the quasi-normal modes, etc.
Okay. No more questions? If no, then we thank Nora again. Start.
Thank you.
Our next speaker is Professor Miriam Mondragon from our neighbor Institute of Physics here at UNAM.
¿Dónde está todo?
Aquí tengo el computador.
Para estar controlado, no sé.
El control
Ese es vigilar, ese es para el video. Este es plástico. Sí, de aquí, pero esa red. Ah, no, tiene.
Sí, tiene tres.
Sí. Este es video.
Entonces no la conecto a la corriente. Espero que no se tiene 60% de carga de aquí, ¿no?
Sí.
Ok. Y ahora sí podemos poner aquí el video. Voy a apagar la...
Esto es con este. Vamos a ver, este me está láser. ¿No?
¿Otra vez?
Nada más le pongo el micrófono. Está permitiendo por delante. ¿Me queda algún bolsillo? Y vamos a ponerse. Lo más al centro que puedo.
¿Ahí? ¿Más arriba?
Está bien.
¿Sí?
Está bien. Sí. Doctor,
So, Miriam is going to talk about some candidates to dark matter from the point of view of particle physics. So,
Okay.
thank you for coming.
So, first of all, thank you very much for the invitation to be here in a different audience. Since I assume that most of you are not particle physics experts, I'm going to give a very brief overview of candidates to dark matter from the particle physics point of view, and I'm going to assume that you don't know a lot of particle physics, so there are a lot of students here, so I'm going to be a ultra mini review on particle physics in something like 5 or 6 slides, yes? And you're free to interrupt me while I'm talking or to wait till I finish. So this is the brief outline of my talk. So what is the standard model and why particle physics, the standard model of particle physics, not the standard model, cosmological standard model, why do we have to go beyond it? How do we use some dark matter candidates? There are lots of dark matter candidates in particle physics. I'm going to mention just a few of them, these, and then I'm going to talk about some summary and challenges. So we all have made these questions if you are scientists. What are we made of? What is everything we're made of? What holds things together? What is the origin of the universe? That is particularly interesting to you. How will it evolve? On what was the physics at the beginning of the universe? So particle physics, cosmology, and astrophysics attempt to answer some of these questions. And of course, we haven't answered all of the questions, otherwise we'd be out of job, or we're doing other things. And they are intimately related. So from the very small, is there something I can do, or is it? Yep, okay. So from the tiniest scales to the largest scales, the structure that we see in the universe, ourselves, and the elementary particles we produce at the lab, it depends on the properties of the fundamental particles they're made of. If the electron charge were different, everything would be different. If the muon mass would be different, we would have a different universe. So we're trying to think that, okay, that perhaps we can go and find out about everything, or perhaps where is our limit of our knowledge. That's what we're exploring between cosmology, astrophysics, and astroparticle physics, and so on. So I'm going to talk now about particle physics. What is the standard model? The name says it all. It's the standard model of elementary particle physics, yes? So it's not a theory of everything, but it's the theory that describes what we know to be the fundamental particles and their interactions. It is based upon symmetries, and this is very important. So quantum field theory combines special relativity and quantum mechanics, Then we have space-time symmetries, rotations, translations, Lorentz and Poincaré transformations. We have internal symmetries, which tell us about the intrinsic properties of the particles, like spin and charge. Some of these symmetries can be global, like space-time momentum, angular momentum, and spin, or local, like the gauge symmetries. We may have continuous symmetries that imply conserved quantities, like rotational symmetry and angular momentum conservation, or a translation with symmetry and momentum and energy conservation. We can have discrete symmetries, like charge symmetry, parity, and CP, the transformations of charge and parity. Parity is the reflection of x, or the coordinates going to the minus coordinate. And all these label and classify the particles. We construct the Lagrangian to be consistent with all these symmetries. And then we determine interactions according how they respect these symmetries and what are their labels under the symmetries. Now, these symmetries can be exact, can be broken, can be a little bit broken, can be hidden, and all of them exist in the standard model. So exact, we want to be special relativity and gauge invariance. They tell us that no matter how we describe our physics, how mathematically we describe our physics or the reference frame we're using, the physics is the same. CP, which is a discrete symmetry, is actually broken. Yeah? So it's there in the standard model, but with a little bit of breaking. So, and then of course there is the Higgs symmetry, which is spontaneously broken by the Higgs potential. So that's how we are going to, how the standard model was made. Oh, I went back. And I put here. Yeah. I use my finger. So this is the gauge group of the standard model. This corresponds to the strong force, SU3 group. SU2 is electroweak, U1 magnetism, electricity, and magnetism. This is SU2 cross U1 is electroweak theory. There are three families of matter, and we know of cosmologically bounds on the neutrino species. We know they have to be 3 point something, but not more than 3.9 or something like that. But also from experiments from the decay width of the set boson, we know they have to be 3. So it's not like we can have an infinite number of generations. I go to what other generations. The gauge bosons are the mediators of the force, and they're bosons, as the name says it, so integer spin. The matter are semi-integer spins, so they're fermions, and the particles acquire mass through the Higgs mechanism. So this is the Lagrangian in a very compact form. And this is our periodic table of elements. So these are the three generations of matter. So the quarks that are inside the nucleus, yeah? Then the leptons, electron and neutrinos, and there are 3 replicas of this, and we know, as I said, that there are no more. So if we add energy to the vacuum, that's as most as we're going to get. We're not going to get an infinite number of replicas of this thing that are more and more massive. So some strange features about our quarks, which are inside the nucleus, is that they are fractionally charged. The electron has charge, as you know, -1, but the up and down, so they have charge -2/3, and these 2/3, and -1/3 the charge of the electron. So it seems that the electron charge is not the fundamental, or perhaps combination of these that give an integer number are the fundamental ones. That is another way of viewing it. Neutrinos, you know all about it, and now of this first generation, we're all, and the rest of the universe, made of. Yep? So everything here is made only of this first generation. We can create these particles in the lab, and we have created them, and these decay quickly into these other ones, yeah? Through the weak interaction. The strong interaction is the one that maintains everything glued by the gluons, the mediators of the strong force inside the nucleus. And here I put here in a little bit corner gravity, because gravity is not included in the standard model. We don't have a quantum field theory of gravity, and this is a quantum field theory. But also the gravitational interaction is a lot smaller than the rest of it, even than the weak interaction. So really it doesn't play a big role there, unless we really want to unify the 4 fundamental forces and think about a unified theory which includes the quantum gravity theory, yes? But the standard model doesn't have it. So it's one of the goals of particle physics eventually to find a quantum theory of gravity, but so far we have this. These are the matter fields, these are the gauge bosons, or the mediators of force, So what they're doing is they're exchanging a boson particles when they interact with each other. It's like throwing a ball. So if the ball is very light, the interaction is long range. If the ball is very heavy or very massive, like W's and the Z, then the interaction is short range. There's the photon, and there's the gluon, which also is massless, but acquires like sort of an effective mass with all the interaction inside the nucleus, because it also carries a color charge. So these come in three different, what we call colors, obviously have nothing to do with what we see with our eyes. There are three different quantum states, and inside the nucleus, these three states are in a neutral combination, so we don't see it unless we probe inside the nucleus, and then we know, because of Fermi statistics, there are three different varieties. But because they come in a neutral combination, they were giving the nice name of like color neutral combinations with the three primary colors. Yeah? So that's the reason of calling them color. And because particle physicists are bored, they say like, okay, well, there are colors, we're going to be very fun, and then we call these are the color and these are the flavors. So when they say that particles come in different flavors, it's just that they come in different types. And when they say they come in different colors, is they have different quantum numbers which are assigned a color charge. So basically that's the standard model plus the Higgs boson. The Higgs boson is crucial for giving mass to all the particles, including itself, because it's not possible to put a spinor with a mass term in the Lagrangian without violating gauge invariance, and I said that I was not going to violate gauge invariance, yes. So many years ago, inspired by condensed matter physics, the ideas came out of making a scalar field, of putting a scalar field coupled to the fermions, and when this scalar field acquires a vacuum expectation value by breaking the symmetry like this is a symmetric state, this rolls down to a circle of minima, let's say, and then this vacuum expectation value is different from zero, and that way the W and the Z bosons acquire their mass proportionally to the vacuum expectation value of the Higgs field. So they have the W, the Z, these are the gauge couplings of the SU2 and U1 group. This is the Higgs boson mass with the self-coupling, and these are the fermion masses with the Yukawa coupling, also proportional to the vacuum expectation value of the Higgs field. So this is crucial to understand the terms of mass, because we knew that the particles were massive, and we knew that the Lagrangian, the Young-Mills Lagrangian, was geometrically and everything very beautiful, but there was not a way to give masses without the Higgs boson, without breaking gauge invariance. So this came to solve the problem, and it has been already found experimentally, so we know that it is correct. But there is a problem with the Higgs mass, which is called the hierarchy problem. The scalar particles are different than other particles. You know, they receive quantum corrections. All particles receive quantum corrections, and the quantum corrections to the mass, let's say, from a particle, is usually logarithmic. So they go like that, you know, there's a logarithmic function, so as they grow with energy, it's going to become like a flat, like a plateau. But the scalar fields, when they acquire quantum corrections, they acquire them quadratically. And then the behavior is very different. It means by going to larger masses, the quantum correction becomes huge, and it stops being like a quantum correction or a correction at all, and becomes a huge number. So if we assume that we have the standard model from, let's say, electroweak scale, which is the mass of the Higgs boson, 125 GeV, to the Planck scale, which is 10 to the 19 GeV, we would have to correct the mass at that scale minus the correction by this factor to give at low scale, at the mass of the Higgs boson, 125 GeV, which I don't know who made this, but, well, it made a service of the community, because these have to be identical up to this, I think is the 30th cipher that has to be cancelled to give 125 GeV. So this is a naturalist problem, very obviously, yes? And there are other problems concerning unitarity bounds, like the theory keeps on being unitary and so on. So we all think, okay, there is a problem, but this is solved if just our standard model is an effective field theory of a more fundamental theory, yeah, at some scale. So that's more or less generally agreed, because there isn't so far a really good solution to the just to the hierarchy problem just within the standard model. If we want to solve this problem, we had to add more particles, and that's the other way, the only way we know so far. Or make the Higgs composite perhaps, but which means again adding more particles because it will be made for a composite state of 2 particles. Then is the problem of the masses. I don't know if you noticed, but in our periodic table, the masses of the, say, of the up quark and the top quark are vastly different. I don't have to go back. You can see them in here. These are 10 to the minus 3 or 10 to the minus 2 giga electron volts, and this is of the order of 172 giga electron volts. Yeah? So there's 5 orders of magnitude, and they both have the same quantum numbers, and they both acquire mass through the Higgs field, the vacuum expectation value of the field, Higgs field, which means that the Yukawa coupling of the top is 10 to the 5 times bigger or larger than the Yukawa coupling of the up quark, being otherwise identical. Now that's a bit unnatural too, not as unnatural as 30 orders of magnitude, but it's still a bit puzzling. And then if you add neutrino masses, which as we know they have masses, then the problem becomes a lot bigger. These are the bounds for the highest possible mass for the neutrinos. We don't know what the neutrino masses are, we just know the difference of the square masses, and the heaviest would be around 10 to the minus 10 giga electron volts. So compared to the electron, which is the lightest here, is another 10 order of magnitudes plus, I don't know, another 7 or 8 orders of magnitude. So our fundamental particles come with a vast array of masses, yeah? So that's a puzzle. And the way they mix, the way they can decay into each other or transform into each other, I said they can decay into each other through the electroweak interaction, is very different from quarks. This is the mixing matrix, and it's very hierarchical. By that means that it's almost diagonal. This is almost 1, the terms in the diagonal, and these are a little bit smaller, and these are very tiny. But the mass matrix of the neutrinos is completely different. It's called democratic because they're almost all the same size, but not quite. If you see, this one is very small. So this is a very big puzzle in the standard model, and there are a lot of research going on about how to get these different CKM and PMNS matrix. And then on top of that is the point or the problem that every particle has its antiparticle. So it is predicted by the theory, but it's not found like a lot or in great abundance in the universe, yeah? So the antiparticle has the opposite quantum numbers of the particle and the same mass. It's usually for the matter particles, but you can also think that the gauge bosons are their own antiparticles. But it's really related to the matter-antimatter that comes together, and they annihilate radiating energy, yes? So we get an antimatter particles from the cosmos, but just a few. We can create them in the lab. But again, the universe we know and we see is made mainly of matter. And again, it's not possible to explain this just within the standard model. Now this is my table where I displayed all the possible particles and antiparticles, the quarks, ups with the 3 colors, the charms, 3 colors, down, strange, top, bottom, and the corresponding antiparticles, electron, positron, neutrino, antineutrino. They could be their own antiparticle or not, we don't know. The 8 gluons, which are with combinations of the color charge, and the gauge bosons and the Higgs boson. So it starts looking less simple, but it still has a definite structure. And so we came to the back side of my t-shirt, where instead of using the ultra-condensed notation, I displayed all the indices, which means color and flavor, so the different generations, and all the interactions among them. And we have to see what part of this back of the t-shirt we do not understand. So, as I said, it's a low effective theory, the standard model. It's a very successful low effective theory. Let me tell you, it's been tested and tested and tested experimentally, yes, and we haven't found any clues or any new physics, but we think there must be, except that where, yeah? So the hierarchy problem I mentioned, the neutrino masses are a lot smaller than the rest of the masses. So if you just put another right-handed neutrino and the Yukawa term, it can be done. But then the natural problems within the little hierarchy problem, let's say within the masses of the fermions, gets bigger. The origin of the gauge interactions, we know they're there, but we don't know where they came to be. And obviously dark matter. Yeah? Then there's the baryogenesis of the matter over antimatter abundance, the cosmological constant, and inflation. So these three relate directly to particle physics. The Higgs sector is not natural, as I said. Yeah.
Okay.
No, go.
Unfortunately, you weren't in this moment, I think.
No, I know, I was not.
Okay, so then I make the question.
Yeah.
Why do you assume that the dark matter, being a particle, has something to do with the problem that now have the theory of OSM? Could be completely different.
Could be.
Could be a theory completely.
That's right.
That don't have.
Could be.
Don't have good. They are very bad. Very not from first principle. It doesn't solve anything, but just make the dark matter.
Yeah, could be that the dark matter problem is not related to particle physics.
Probably could be, but when you look at the other, the big candidate, you see that maybe it is, because the big candidate, astrophysically, they have a lot of problems.
Yeah.
The actual dark matter in the universe. So the idea that dark matter is what we need from theories, standing from the current theories. Okay, science, physics has been for 300 years in which the problems from theory were solved from observation or from detection. But in this case, maybe it's not the case. So all the problems you are saying very well may have nothing to do with the
that could be. Yes, that could be. That could be that is a different question. So I said, I'm going to assume, because it's an assumption, we haven't observed dark matter in particle physics, yes? So there could be another completely different solution, but I'm going to say, okay, we have to go beyond the standard model anyway, because that we have to do, absolutely. And some of these were motivated extensions. There is not yet a theory beyond the standard model, because there are many problems which I didn't put here. If it were, we would just be testing that theory which solves all of our problems to see if it also solves the dark matter. And if it didn't, we would say it comes from somewhere else. So what I'm going to say now is that some of these motivated extensions have some dark matter candidates, but every single one of them has a problem or several problems in them. And that is the point, I think, of what I want to stress. Many candidates, and we haven't got a single theory where we can cover everything at the same time, yes? So it makes the problem very difficult. So, okay, so let's see the nature of neutrinos, the Dirac-Majorana, the origin of electroweak symmetry breaking, the strong CP problem, the number of generations, and then more through cosmology, not enough CP violation in the standard model for baryogenesis, the value of the cosmological constant, inflation inconsistent with non-zero baryon number, and if dark matter were a particle, then which one? Yeah? So these are a few of the questions. What are 3 generations? I said there are only 3. We know by cosmological and particle physics bounds there are 3. What are the masses of the particles so different? I've already stressed this problem. There is no CP breaking in the strong interactions. That's odd, because if you just write the Lagrangian like that, there could be a lot of CP breaking in the strong interactions, and so far none has been observed, and we assume there are bounds, so we assume if there is very, very little. What is dark matter? Is it, as it's been discussed right now, might not be, but what is it? Why is there more matter than antimatter? So evidence of dark matter comes all from astrophysical observations, yes? But I said we want, or that our particle physics describes the universe as it is. So, okay, what Zwicky proposes are the kind of matter that is not luminous. You've heard all about it because that's what you've been doing all these days and previously. And there is evidence in kiloparsecs in galaxies and clusters of galaxies and all the way to the anisotropies in the cosmic microwave background. So if we assume that dark matter is a particle, what we could infer from the fact that we have all these astrophysical observations. First, that is electrical neutral, that is non-baryonic, not made of protons or neutrons, that move very slowly during formation of the first structures, so it's slow or cold, and has a mean lifetime longer than the age of the universe, otherwise it would have decayed and we wouldn't observe it right now. So that favors cold dark matter. And you know all the problems of cold dark matter. A large structure is okay, and the small structure is not okay, yeah? So we assume that it comes from particle physics, and we see, okay, from what we know, could it be a particle? So if we assume there is a particle, this is the first, besides the neutrino masses, the standard model is constructed to not have neutrino masses, but it's very trivial to put them very simply. I mean, it gets a small hierarchy problem, but you can put them. So it will be the first proof that there is new physics. None of the standard model particles can account for 100% of the dark matter, precisely because it would have been cold, and the other candidate from the particle physics point of view without extending the standard model would be the neutrino. So that's discarded. So better explanation from particle physics requires new particles. So something that is there in the dark matter halo. So what do we know from dark matter from particle physics? This is the PDG, the particle data group. If you print it, it's like a fat book like that. It's lots of all the information we have about particle physics and searches beyond the standard model. And that's the page of the PDG. So dark matter mass, don't know. Mean lifetime, don't know. Isospin, don't know. Decay modes, don't know. So basically, from particle physics, we know nothing, yeah? Because the evidence we have is indirect. And we want it to be a particle. Let's see, why? Because when we go beyond the standard model, as surprises, they come things that could be candidates to dark matter. So let's say, first, how do we go beyond the standard model? So we have a problem, okay, it's an effective theory at low or lowish energies. So what we have been doing is add symmetries, particles, which means fields, or interactions. Usually these three are related. We can add extra space and dimensions, basically space dimensions, like in string theory, follow some fundamental principle, which we might like, or we might think that we know that's the one. And many of these are related, obviously, but should provide a partial solution. There's nothing that has provided a solution to all of our problems, so we aim at least partial solution to some of the open questions of the standard model. So that's been the quest. So some of the standard model extensions give good dark matter candidates. There are lots of dark matter, beyond the standard model extensions. So we have lots of dark matter candidates. They can be fermions, scalar, vectorial, you name it, you know. They can be, basically everybody with a bit of imagination can come with a theory or a model of particle physics with a dark matter candidate. The mass range is vast, so I call them from the ultra light to the super heavy, like in boxing, from 10 to the minus 22 electron volts to 10 to the 2 TeV. If they're thermal, if they're not thermal relics, then they can be much heavier, 10 to the 16 or even 10 to the 19 GeV. And it's notoriously difficult to detect. So you can make direct production, a collision of protons and antiprotons like the LHC to produce two pairs of dark matter candidates. Indirect, when these annihilate and create two particles of the standard model, particle plus antiparticle, or like in direct detection when you have a dark matter particle hitting, say, a nucleus, and the recoil we can measure. And there they are, our ultralight, super flyweight, and the super heavyweight from 10 to the minus 22 to primordial black holes, and composite dark matter here, which are very heavy. I'm not going to talk about composite models. I'm going to talk just like the ones that come from particle physics without compositeness. So here we have axions and axion-like, which are popular now, from ultralight to light, so 10 to minus 22 EV to keV. WIMPs, which are the ones that have been more studied. I just read that, like people, they tend to populate landscapes. Yes, so there are lots of candidates for WIMP physics, and that's because of the electroweak interaction. If it's going to be extension of the standard model, many of the extensions have electroweak interaction in the new particles, so it's not so surprising. But here we can be SUSY particles like the neutralinos, or Kaluza-Klein particles that come from extra dimensions, lots of Higgses with or without SUSYing, sterile neutrinos, which we need anyway to give masses to the neutrinos. And these are thermally produced 100 GeV, 10 GeV to 100 TeV. There's a zero, extra zero. They're super heavy, they're primordial black holes. WIMPzillas, which are some particles which are produced non-thermally after inflation. I'm not going to talk about that, but it's possible to invent a WIMPzilla, which can be also dark matter, or super heavy particles, compact objects. So you see, we have more than one challenge. And so in our beyond the standard model physics, yes? And here are the mass scales. Again, these are the ones that are very well studied. Super WIMPs are a bit lighter than the traditionally WIMPs, axions, neutrinos, and these are the composite objects, and these WIMP-SILAs I was talking about, and this is the fuzzy cold dark matter that is very, very light. So the usual way, as I said, is to add symmetries, which has been useful right now, and it might be the way to go, all to a more fundamental theory or not. But that's the way it has been proposed and successful so far, by unification, electricity, magnetism, and light, and electromagnetism, beta decay and neutrino interactions, weak interactions, electroweak interactions, and the standard model. Then the strong interactions, and we have here what we know. And then here we can go by adding more symmetries, adding more particles, adding more fields, adding extra dimensions, and then we can unify these with the terrestrial gravity and celestial mechanics with the universal gravitation, space-time geometry, general relativity, and ultimately we would like to have something here. Bear in mind that there are many people saying that perhaps gravity is an emergent theory, and other people who are saying that perhaps quantum mechanics is an emergent theory. Yes, that leaves us like, okay, it might be not possible to unify them, but there's a quest for doing this. But at least these three, the gauge interactions, have similar properties. So it's not difficult to unify them in a grand unified theory by adding a lot of more symmetry. And this is how we would be realized in the universe. So we would have the Big Bang, inflation. Here we have the higher energy cosmic rays, 10 to the minus 10 seconds after the Big Bang. This is where the accelerators, LHC, Tevatron, and RIC, are probing the energies, yeah? And then we have to the 10 to the, say, minus 5 to 10 to the 2 seconds, it starts to form bounds and nucleus of quarks. They start binding quarks. And here we have to start forming more particle physics structure, atoms here, and then we can start with all the structure formation of the universe. So if we want to go and test our theories, we really have to go to very high energies, and that's why we're constructing these huge machines like the LHC. But we are getting to a limit of what we can do, and we're all turning to astrophysics, which is naturally a way to find very high energies, yes? Now, the problem is in the lab, we can control what we're doing, and in astrophysics, we just have to wait and see what happens and measure what we receive. So the neutrinos have masses. This is really interesting news, yeah, for both cosmology, astrophysics, and particle physics, because they're absolutely relevant in Big Bang nucleosynthesis, in the core collapse of supernovas, and obviously in what we find in the lab. So the most favored way of giving masses to neutrinos is assuming that the right-handed part, which we need to form a Dirac or a mass term, is very heavy, and they also can be their own antiparticles. So we have large Majorana masses plus a Higgs, and then induce small, like in a seesaw, small Dirac masses at low energies. But it's not the only explanation. You can also generate neutrino masses radiatively, all through non-renormalizable interactions from a theory which would be non-renormalized interaction in the standard model, but perhaps renormalizable in a more complete theory. So this is the one that most people use, and it's let's say, elegant and economical without going to too much trouble, but it's not the only one. And then right-handed neutrinos have been proposed as dark matter candidates. They are sterile, electroweak interactions, and only coupled to left-handed particles, so they could be candidates to dark matter, but, it will be one dark matter, it will be near thermal, so it's not thermal, and although they have a wide range of masses for the right-handed neutrinos, not only a few of them, which are more or less in the range of KEBs, can be dark matter candidates. So we need neutrinos, we extend the neutrinos, and as an extra plus, we get a dark matter candidate. Okay, let's have a look at how good a dark matter candidate on your right-handed neutrino can be. And it turns out that if we only add one, then it could be a good candidate only in the KEB range. If we add more, then of course all these bounds are relaxed, and we could have a more complicated structure of the PMNAs, or the mass matrices of the neutrinos, but basically more or less would be in that range. So they are constrained, and they are also constrained with only one right-handed neutrino for searches in the decay line X-rays in the mixing angle versus the mass plane. So this would be our allowed parameter space, and this would be the preferred line where we could have that neutrino I just showed. So that's adding more particles. Now we are at more fields. As I said, there's no CP violation in the strong sector, and this is known as the CP strong problem because in principle there could be more. And in 1977, Roberto Peche and Helen Kuhn came with an idea of promote a term in the strong Lagrangian, the QC Lagrangian, to a field. And very similar to what happens in the Higgs field, this field acquires a vacuum expectation value, and Q's, this CP breaking is because of this extra symmetry, is forbidden, and we would have a very, very light pseudoscalar field, complex pseudoscalar field with a very, very, very small coupling, and then that would explain why there is no CP violation in the strong sector. Now, so far, there are a few other explanations to solve the CP strong problem, but this is so far the most popular. Again, there are a few more exotic, and this was called axion. They say that it was Wilczek who gave the particle its name because it's like the soap, the dishwashing soap. I don't know if it's true or not, or it's because it's a pseudoscalar, I don't know. But surprised later on, they realized in the 80s that it could be a good candidate to dark matter, except that if we take the axion of the CP problem as just 100% of dark matter, the relic density is very small. So if it's created non-thermally at the end of inflation, then it can be, might be 100% of the dark matter, and then it has a very, very light mass between 2 and 20 microelectron volts. Now the nice thing about axions is that they're slow, they're bosons, and they can form condensates. And they leave, because they form condensates, they leave their imprint in structure formation. So right now, axion and axion-like dark matter is very, very popular.
With the mass much smaller than
that's what this is probing.
If we want to make galaxy, you have to have 10 to minus 23 electron volts.
Yeah, if you want to make, yeah. This is just axion, not axion-like, but just plain axions. CP strong problem.
So, not that matter.
Just very, very small range, because you also have star, the supernova, and this inverse Primakov effect in dense objects, yes? So if you want it to be the CP axion, then it is almost ruled out as 100% of dark matter. Could be 3 particles, the axion particles in the halo. Okay, but if you really want 100%, the normal CP axion is ruled out. They are probing now for axion masses of this range of mass, and they haven't found anything. So K axions are very nice. It could be, but again, not 100% of the dark matter. Then we go to WIMPs, weakly interacting massive particles, which are economical. They are thermal relics. The density of early universe and relic density depend on few quantities. The interaction is weak between the dark matter and star-mooned particles, and they will be between 10 GeVs and 10 TeV or 100 TeVs. I think I keep on moving the zeros. And the mass and interaction strength coincide with electroweak interaction, which is what's called the WIMP miracle. You could have KeV to 10 GeV light dark matter with constraint, or what I just showed, the previous one, it would be non-thermal to make it 100% dark matter, but very challenged, let's say. So again, now I have more symmetry, and for many years, this was the vanilla candidate for WIMP particles, LSP, for WIMP dark matter. So you had a lot of symmetry. You had a symmetry between bosons and fermions, and you say, and also I have a grand unified theory. So I use SUSY-GOT. So relates bosons and fermions, supersymmetry. You have, the minimal model has 2 Higgs complex doublets. So when electroweak symmetry is broken, you have 5 massive scalars. You say, okay, and also one grand unified theories, only one fundamental interaction. I join all of them, and then I get something which gives me a solution to the hierarchy problem, because the bosons and fermions, since they are related, the contributions to the radiative corrections to the scalar masses cancel exactly. But we don't see supersymmetry, so it has to be broken, and therein lies the problem, yes? Because the only nice way, without disastrous phenomenological consequences, we know of breaking supersymmetry is with breaking it softly with the soft supersymmetry breaking terms. I'll call it the soft terms. And the masses should be a few TeV. That's our prejudice, because we want it to be a solution of the hierarchy problem, yeah? If the solution of the hierarchy problem is other thing, then supersymmetry could be all the way to the unification scale or somewhere else in between, yeah? And then the surprise of having supersymmetric GOTS is that, well, with the GOTS, we can explain the fractionary quark charge, the Weinberg angle, predict approximately some mass ratios. So we learned some things. That's what we want from a more fundamental theory. But it had other problems, which is probably fast proton decay through leptoquarks. A lot of other parameters when we break supersymmetry. We went to the economical, but we added more parameters otherwise. Only one fundamental interaction, which is nice, and several dark matter candidates, some of them better than others. So it's like, you know, this reductionist principle goes also to camping with a spade, which is a mixture of a spoon, a fork, and a knife. So the dark matter could be the lightest supersymmetric particle because we have a symmetry between the non-supersymmetric and the supersymmetric particles, which prevents the lightest to decay into normal particles. Has to be electrically neutral. There are lots of candidates there. Direct detection will be by collision, like here. Indirect detection by missing energy, like two particles of the standard model then created missing energy. And we would have some astrophysical observations. And now here I want to stress a bit about the SUSY breaking, because normally everything, all the SUSY searches are doing in a limited number of parameters in a very simplified model, because that's a sensible thing to do when you have a very large parameter space. But here what I want to stress is different ways of breaking supersymmetry lead to different predictions. We have lots of ways of breaking supersymmetry, and so far we've been obsessed with the constrained MSSN, which has only 5 parameters and inspired by minimal supergravity. But we have a lot of other models which also have good dark matter candidates, but they are inaccessible to accelerators. So if we want to access those regions and test these models, we have to go to indirect observation from cosmology and astrophysics.
Also direct.
Also direct, yes, but then we have bigger accelerators, yes?
No, also from...
Yes, direct, on the ground, yes, of course, yes, direct, like hitting, yeah. But then, the higher you go in mass, the smaller the sigma V goes, yeah? So at some point, they hit the neutrino floor, yeah? So it might be there, we don't observe it, and instead of being, I don't know, 100, it would be 3, but okay. So people usually distinguish this between the bulk region, which is associated with light leptons, focus point region with Higgsino mixtures, the partner of the Higgses, co-annihilation region where they're co-annihilating with the neutralino with the next lightest supersymmetric particle, or the Higgs funnel where they are close, the neutralino, to one of the pseudoscalar Higgs. I just want to show this because there have been extensive searches of what could happen. This is the constrained MSSN, and this is M1/2 is one of the soft breaking parameters, and usually the light supersymmetric particle, say the neutralino, will be half of this mass of 500 GeV. So this is the region. This is the region that the LHC has probed. If you changed a bit your model, let's say the non-universal Higgs masses, 2 different versions, or you say, look, I just want a phenomenological model, and I just see which parameters are correlated or not, and you turn 10 of these parameters is the PMSSM10, then naturally the mass of your lightest supersymmetric particle moves a lot higher out of the reach for the LHC and probably even for the next accelerators. But anyway, here is the sigma versus the mass of the neutralino in these regions, and again you can see that these are the different ways that the dark matter can be produced, and these are best fitting points, yeah? And here is the projection of LZ direct dark matter detection experiments. And this is just assuming a slight variation of the SUSY breaking scale. And there's another thing, is that if we're going to do these very sophisticated searches, we, the theoreticians, should work also a bit harder. And what they show here is, okay, they put some difference of stop lines, which is the blue line, where they know that dark matter density corresponds to observed by Planck and W map. This is the Higgs mass, this is the experimental, the orange Higgs mass, and this is what you can calculate with the spectrum generators and Higgs masses. And you can see that if you start putting all the loop corrections or the radiative corrections just to the stop masses and the top mass, then the favor regions go very high. They're still possible, but very high. This is the mass of the neutralino. 5 TeV for some of the parameters, 1 to 2 TeV, and so on. This is just to show that it's a matter of a lot of work, both theoretical and experimental. So SUSY is solution to the hierarchy problem. It's the only extension of the Poincare group, so it's nice. Several dark matter candidates, I just showed the neutralino, but they have others. Can be gravitino, can be exino, is neutrino. I put in light blue the compatible unification of couplings and unification of couplings compatible with scales of seesaw mechanism, because this is okay, that the model is consistent with some more general assumptions, but it's not proof of existence, just consistency. And if these are not valid, then okay, this is something else. You can break our parity, and you have gravitino as dark matter, is practically undetectable. But more models than the constraint NSM should be considered. And if you think that it's unnatural, it just might be hiding unknown physics. It is unnatural. It doesn't have neutrino masses, and it doesn't have an axion. So the MSSM really should be complemented, again, with a mechanism to generate neutrino masses and for the strong CP problem. And the loss appearance, well, we examine how you build the supersymmetry, where the expectations came, and where you have to look everywhere at higher energies. So that's basically what I just said. And in the last few minutes, I go to the rest. You can add more particles. You can add multi-Higgs models without SUSY, yeah? These are also very interesting. They don't cure the hierarchy problem, but they provide a solution, possible solutions to the hierarchy between the masses, both in the quark sector and in the lepton sector. You can add singlets, or you can add doublets, yeah? You can look for missing energy in colliders, and if you have the lightest component neutral and a discrete symmetry that prevents it, like in the R parity in the standard, in the MSSM, you have a dark matter candidate. The 2 Higgs doublet model has been extensively studied, and the real Siglent extension, for instance, if you want to be super economic, is almost discarded, yeah? And the inner doublet model is where you just add one more Higgs, which doesn't couple to anything. It's just like a dark matter candidate you add, like, with some symmetry. It is also challenging the 2 Higgs doublet model, but it has very interesting features. It can also be a dark matter candidate, but also has to be heavy. So bottom line, if they want to satisfy both all the Higgs bounds at LHC and at LEP, plus this is the limit on the relic density, yeah? Then what you see is depending on how your extra Higgs particles are, you're going to have to look for heavy dark matter particles, and the same here, yeah? Not super heavy, yeah, 100 GeV, and here, for instance, you can go all the way to TeV, and here, if this is for a certain model, if you go to more than, say, 1 TeV, then you'll be out of the dark matter relic density bound. You can add more dimensions. You see, like, these are just a few samples of a few theories, yeah? So the more popular ones. You can add more dimensions, and this is not the new idea. This is from Kaluza and Klein 100 years ago. They started with a theory of Einstein gravity in 5 dimensions, and they found that if they compactify in a circle, they can unify gravity with electromagnetism. This theory has many problems, but it predicts a tower of massive scalars, which it's like with an n number here, so it's 1, 2, 3, 4, 5, so an infinite tower of massive scalars. And the parameters of the two theories are connected since they have the same origin, and this is the basis for more extra dimensions, more modern theories, called universal extra dimensions. And this massive tower of states, the lightest one, provides also for a dark matter candidate. Okay, this was not an idea of Kaluza and Klein. Obviously, this was something that was noticed later, yeah? And the good thing is they can be tested, because we can have the nicest candidate. If we cannot test it anyway, then it's not a good candidate, yes? So the Kaluza-Klein photon would be a WIMP. The Kaluza-Klein Seth boson would be a WIMP. Kaluza-Klein Higgses in non-minimal scenarios can also be WIMPs, yeah? You can make them with or without supersymmetry, the way you like. Rapid proton decay is forbidden, which is a plus. And then you can have a stable electrical neutral non-color particle, okay, non-color particle, and there are limits for this. So, okay, again, this is the relic density, and these are different types of Kaluza-Klein models. Yeah, this is the mass of your Kaluza-Klein particle, is Kaluza-Klein photon or a Kaluza-Klein Seth as a dark matter particle, and this is the relic density in different 5-dimensional universal extra dimensions. The black lines are the mass splitting between the Kaluza particles and the Kaluza-Klein quarks, and this is the green band. So all these could be possible good candidates for dark matter. Again, notice that they are very heavy. The lightest is 500 GeV, but they can go easily to higher values in the TeV range. And of course, adding extra dimensions takes us to string theories and gravity. Unfortunately, we don't have, as I said, theory beyond the standard model, because string theories lives in 10 and 16 extra dimensions, which have to become compactified to our 4-dimensional world, and as far as I remember, something like 10 to the 500 ways of compactifying that, which is bigger than the number of protons in the universe, so we really don't know. Still, it's a really interesting theory, and as surprises, it comes with the unification of gravity. Many of them have supersymmetry, extra dimensions, a plethora of new particles, because the symmetry group is extremely large. And of course, if you have supersymmetry as a lower energy limit, you would have the neutralinos and everything there that goes in supersymmetry as dark matter candidates. But recently, it has been shown that they might have also ultra-like, axion-like particles that come with the extra U1s that are in string theory, and they are very natural in these string compactifications, a lot of very ultralight scalars, and it's called fuzzy dark matter, thanks to this Bakana-Gruzinov. And then locally, many people have been studying these ultralight particles, but more from the gravity point of view, just like classical, very ultralight particles like Darío, Antonatiu, Alma Gonzalez, and many other people here. So this is right now very appealing, because it solves several problems of structure formation, and very recently, it has been shown that yes, this formed these filaments in early galaxy formation, this by these authors, of which Jesus Zavala was a student here. So ultralight scalar axion-like particles, they are good dark matter candidates. And here, this is a bosons, because they can form condensates, they make like these caustics, yeah, and then they leave a footprint in the structure formation, yeah. So as you can see, we have a vast array, yeah, I just showed a few, of what particle physics proposes for candidates to dark matter. But there's a caveat here. Most of the models assume that is 100% of dark matter is just one particle and nothing else, yes? You can build models where you have, from particle physics point of view, there is no problem building a model where you have 2 or even 3 or more dark matter candidates, provided you know it's baroque if you want, but then you can have the right symmetries to prevent it from decaying, yes? The challenge comes when you want to put that in a cosmological setup and not spoiled big man nucleosynthesis, starting with the structure formation and all the rest, yeah? So you can have SUSY models, non-minimal SUSY models, multi-Higgs models with discrete symmetries. But the other thing that people don't, they start with a low energy model or with a high energy model, but is, as far as goes, there are few attempts to really try to meet with the 2 models, getting the input from astroparticles and cosmology. See? So there's a lot of work there. So the summary is there are many dark matter candidates in beyond the standard model theories, WIMPs and non-WIMPs. Heavy candidates are natural in some models, but might be unreachable, so we have to look for indirect signatures, direct detection, and so on, yes? Very light candidates might also be unreachable, yeah? So we have to go again for indirect ways of looking for them. So there are different perspectives and advantages. As I show you, add this thing to solve this problem, and you get the dark matter candidate. Oh, that's nice, then you have to go and see if your dark matter candidate is actually good or not. But studies, both theoretical and experimentally, usually assume only one dark matter type, and all the information the astrophysicists give us about the distribution and dark matter profile in the galactic halos. So from the particle physics point of view, what we want to look is for models which are not one-trick pony, but which solve several problems, not all problems, because that is a very vast challenge, but at least more than one problem at the same time, with few assumptions, and that respect all experimental and observational data. And then here, not only the bounds that come from the direct detection or direct production in the LHC, but also from astrophysical and cosmological bounds. So, say 10, 15 years ago, people wouldn't worry too much about this, but now with the cosmological and astrophysical uncertainties getting a lot smaller, it's absolutely a must. Candidates depend strongly on models and assumptions of only one dark matter candidate on the details of the model. But it's difficult to do searches with model-independent quantities, yeah? So there are models with more than one particle now, but there are very few, so we need to build at least a couple of realistic ones, which are good, and test them in cosmological or astrophysical setups, yes? Because we're assuming that this is the physics beyond the standard model. So we need a combination of direct and indirect searches. We need more realistic, so from the particle physics point of view, obviously we have to build better models, yeah? But we also need more information from astrophysics. We need more realistic halos. We need more information from astrophysics and cosmology, from everything, to characterize better dark matter. See, so what are we looking for? How is the distribution in the halos? It's really the density, the local density is really as it's supposed to be. What are the uncertainties? I don't have a transparency here, but in HAWK we are looking at specific models to see if we can discard them or not, or put sets. And what happens is that you have a factor comes particle physics where you know the uncertainties very well because it's quantum field theory and some models which you know. And then we have to put it together with an astrophysical factor, the J factors, which have a large uncertainty. Yeah? These same assumptions are the ones that are used to calibrate direct detection experiments. So if there is a large uncertainty there, us particle physicists which are not aware, well, we are aware but might be much way out that we are thinking, we might be calibrating or looking for in the wrong regions, yes? So it's really important to have all this astrophysics and cosmology part for us much better understood to build more realistic models. So all the uncertainties better determined. And for us, it is also important to build models which are a bit more challenging, going a bit beyond the more simplistic models, and thinking for putting input of astrophysics and cosmology if we really want to insist that dark matter is a particle, and how much of dark matter is a particle we are willing to put in there, yeah, to see how this can be. So there's a lot of work for us ahead as a community, and well, you're all welcome to chip in. So thank you very much.
Thank you, Miriam, for this very nice talk. We have some time for questions. Ms. Paula.
Okay, so I would like to give a view from a physical point of view.
Very good.
Okay, so then the first thing is then let's see what happens where the matter is. So
Yes.
in galaxies.
Yes,
The
yes.
effect of galaxies, you see the dark matter.
Yeah.
And I would say that we see there are also that this matter, dark matter, maybe interact with yourself or interact
Yes.
with values.
Yes,
right?
that's right.
So you have put enormous amount of models.
Yeah.
But for instance, ULA and barrier and condensate, they have one difference with respect to all the others.
Yeah.
So they really, it's not true that the matter doesn't interact with itself or is not in collisions.
Yeah,
It's very,
that's
very
right.
collision.
That's right.
From a physical point of view, you can like or you can not like,
Yeah.
but that matter is interactive.
Yeah,
Okay?
that's right.
And how, we don't know.
Yeah.
Okay, so this, but most of the wind, so they really can produce the galaxy as we are. So if the dark matter is collisionless, so it doesn't interact on a small scale in certain way, cannot reproduce the data. The data are increasing exponentially in the last year. I really advise you to look, publish papers on physical review, nature, and so on in the past 3 or 4 years. And we see that most of the astrophysicists thought that wind are data, okay, from this point of view. Any kind of parameter that you use. Because we see in action the dark matter at small scale, and people like that you are shown are looking for fuzzy dark matter because in this way they have a sort of interaction.
Yeah.
Fuzzy dark matter has a problem, okay, also, that can produce galaxies only small, galaxies like dwarf galaxies. We have problems, and we have cores, and also in very, very big galaxies, and so fuzzy dark matter at the moment doesn't know how to do this.
Okay,
This is
yeah.
one problem. And many astrophysical point of view, they think, okay, for 30 years we have used the first principle, and then we can get the matter from
Yeah.
what they have said at the relation. Now we stop, we are looking for the matter by our own, and looking at the properties of the matter, which are very, very strange properties. The interaction, for instance, the density of the dark matter is related in a galaxy with the density of the luminous matter in a certain way.
Yeah.
This may something on the phase space of the dark matter density. So the idea is to stop, let's say, the paradigm, to start to look what is really dark matter behavior where you detect, so in galaxy, in clusters, and from there to try to infer the scenario for dark matter.
Yeah.
Okay, and of course, when you get to a certain point, you need also theory, not
Yeah.
theory. But at this point, the scenario cannot be because we have a problem with standard model, and so this will help us to detect this particle. But as to be said, we found incredible things in galaxies, in clusters, in the universe, in the CMB, that direct us towards this particle.
Okay,
So
yeah.
from observations, now,
Yes.
not from theory.
Yeah.
Okay? This is my idea. It is the idea that many, many other
Yeah,
astrophysicists
yeah.
have today. Okay?
Yeah,
That this is-
but that's exactly what I was aiming at. The particle, the dark matter particles, candidates we have, they just came. They came as a plus, There was not a theory that was built to make, but they came like, oh, it could be a dark matter particle, and many people still look for dark matter candidates like that. Yeah, so it came like that. But what I stressed is that all of them, come like. Because we want to solve one problem in the standard model is like, oh, we have an electrically neutral stable particle, it could be dark matter, yeah? So that's how they come to be. And they are very simplistic models, all of them, yeah? So just looking around at our universe is probably much more complicated, yeah? So that's what I'm trying to aim at.
Many dark matter. So
That's
one is
exactly-
the dark matter that makes the galaxy.
That's exactly what I'm trying to get at.
And one is the other.
That's
which
exactly-
solves other problems.
That's right. That's exactly what I'm saying. In particle physics, we've been concentrating from one type of particle, the one we like from our model that came out to be electrically neutral and stable, and then try to fix everything with that thing. But then if you look around us, it's, just look at the standard model, there's not one type of particle, not even the Higgses are probably one type of particle, yes? So that's what I said, we have to build more realistic models. We have to build models which, we have to do it anyway, yeah. And we have to think of more than one dark matter particles that do different things in the galaxy at different times, yeah. So you could have one completely stable and one very long-lived dark matter particle that at some point was there for some kind of galaxy formation, then decayed somewhere, yeah. So these kind of models are just starting in particle physics to be made, but so far they haven't. And what I'm saying is exactly that all the models we've been looking at solve one problem here, and they gave us like a nice candidate, but they are very unrealistic. Yeah. On the other hand, we have very, very powerful tools because we have quantum field theory, so we can really go and know how to calculate all the sigmas and so on. So that helps us, let's say, but we need more information from other points, and we have to build more complicated models as particle physicists, yes, that take into account this dark matter interaction, decaying dark matter, different dark matter decaying at different times, and perhaps a dark sector which just interacts with itself and doesn't have anything to do with us, and if we could have any possible, inkling of how to detect that. That's exactly what I was trying to say. So we need a lot of interaction between astrophysicists and particle physics. And the last thing I was to say is like, we can get very high precision measurements, and we need to really see throughout the models we are building and going to build, we need also to know more precisely all the part of the astrophysics. Yeah. So because we need to be able to discard models which, not to be wasting time on models which are like, okay, this is completely killed by that. So that would be my message too.
Okay, more questions, comments? So I have a quite general question. It is clear that you have different points of view, from your personal point of view, from the point of view of observations. This is you're an expert. You're an expert in theoretical physics from the point of view of elementary particle physics. What your recommendation is very clear. So people go ahead and try to observe better the effects of dark matter so we can understand better the properties of those particles we don't know. What would be your recommendation, especially for young people? Because now we see that there are so many possible models. There are so many candidates. What would you recommend, especially young people here sitting in the auditorium? What should they do?
Look, I try to stress, if you notice, I don't know if you notice, I always put the experimentalist graphs. I'm a theorist, but I always look at the data. So look at the data. So if your neutrino prediction is 10 GeV and not a single experiment at that energy in the reactor experiments or something gives you that kind of neutrino, is discarded. If you have a very nice unification model and the Weinberg angle is way off, it's discarded. So you really have to know from the particle physics point of view what you're trying to describe. No matter if you have the most beautiful theory, you have to know your phenomenology. And for the astrophysical part, it's exactly the same. Yeah, which he was saying, okay, what is it telling us about structure, about bounds? And you have to know, the other thing that is difficult, what I think every theorist should know, is how are the experiments set up? So what were the assumptions done when you put your xenon 1 ton? And what were the assumptions? What is the background? What were the assumptions on the models? What is the sigma v they're assuming? What's the models they are calibrating the detector? Because that can tell you what are you looking for. Yeah. So no matter if you're theoretical physics, you have to know your physics because that's what you want to describe. Yes. So you have to know. In this case, it's a bit more complicated. You have to go and know what the particle physics bounds, and you have to know what about the cosmology and how the astrophysics. So it's really difficult for one person to know everything, and that's why I'm saying we have to talk more about between each other to say like, okay, this points to this points to that, and then like I said, oh, but I have when someone told me, oh, we could explain this with neutrinos and so on. I said like, yes, but no terrestrial experiment has detected neutrinos at that scale. So where would they come from? Yeah. So those are the questions that we have to be talking about. Yeah. So if somebody else proposed from astrophysics point of view, oh, we have these interactions, they're like, yeah, but these particles don't interact that way, for instance. Yeah. So that would be.
Okay. So thank you very much for the talk and for the discussion. 15 minutes. 15 minutes.
Lo hacemos en persona.